Ilian Iliev's lectures, it will be mostly based on how to do radiative transfer, particularly from the point of view of epoch of reionization and cosmic dawn. Yeah. Ilian. Yeah.
So hello everyone. So I'll talk to you about radiative transfer, starting from the very basics. So if you have seen this before, I know a few of you at least have. Well, it's a refresher. If not, well, even better than it's new. So starting from how you define the basic radiative quantities. So the most basic radiative quantity that we want to define is so-called intensity, which is if you take an area, some small area, and you calculate, okay, how much energy passes through this area per unit time, per unit in a particular direction, so per unit solid angle, per unit frequency, and of course area, then this is the intensity. So that's just the energy that passes through in a particular direction per unit time and frequency. And I have indicated here that it depends on frequency because there is also frequency integrated one, which you can define, which we'll do later. Okay, so this one you probably have seen before, but it's a basis of everything, so it's important to get it right. And just to remind you about the solid angles, because I know sometimes they are discussed, sometimes not, just very quickly. So solid angle is basically defined as area divided by the r square of the distance from the center of the sphere. So small area, and then of course the solid angle in spherical coordinates you can write the usual way. And very often you also define cosine theta to be something called mu. So then d mu will be the sine theta d theta. So the whole solid angle is just d mu d phi with the minus sign because of the derivative. Okay, so getting to why is phase space, why is the intensity so useful? First, we'll connect to something called specific intensity to the phase space probability density of photons, which is another way to describe the photon field. So if you calculate the phase space, so the phase space probability density is just what it says. It is the chance to have a photon at a particular place in space and a particular momentum p. So if you take the phase space density, multiply by the volume, a little volume of space, and a little volume of phase space, which is the momentum space, and you sum up over the two polarizations of the photon, you get how many photons you have there in this small volume. So that's in a 6-dimensional space in momentum and physical space. And then if you remember that momentum, in momentum space, you can write it again in spherical coordinates, but in momentum space. So you get p squared instead of usual r squared, dp, and then the d solid angle. And the p, of course, for photons is just h nu over c. So you can write it in terms of constants and d nu d omega. And volume in real space is, of course, just the area times the distance it passes per unit time, which is, of course, speed of light times t. So length times area gives you the volume. And when you combine the two, you can see that this and this are essentially identical once you take into account that d is h nu dn. So the specific intensity is directly related to the phase space density. So there are just two ways to describe exactly the same thing with some constant in front, which needs to be there to get the dimensions right. All right, so what can we do with it? Well, using this, you can describe pretty much any radiation quantity that you can think of, one way or another. So for example, let's say you want to calculate the energy density of the radiation. How would you do that? Well, you take the phase space density, which gives you the probability for a photon to be somewhere in phase space. Then you integrate over all the momenta because you don't care what momentum the photon has. You add them all up. And of course, you need to multiply by the energy per photon. And the whole thing is, of course, just, you can see that this is just the density of energy. That's the total energy per unit volume. And you can, using the connection between phase space and the specific intensity, you can also write it as specific intensity integrated over the solid angle and the frequency. And there is 1/c again to make the units correct. And of course, you can define also energy per unit frequency. So this is the specific energy, which is the integral of the specific energy over frequency is, of course, the total bolometric energy, where, of course, bolometric just means we add them all up and we don't care what energy it is. You can also do vector quantities. So for example, flux is a vector quantity because it's the how much of energy flux is how much energy is flowing through particular place. So how you calculate fluxes generally is you multiply the velocity of the quantity that's flowing by the quantity that is being transferred. And then again, you need to integrate over all momenta and sum up over the polarizations. And again, you get easily the flux of the photons. You can also do the energy flux in a particular direction by just projecting in that direction. So if the angle between the area and the flux direction is theta, you get additional cosine because of the projection. You can also do a momentum flux in a particular direction. So in this case, you project both the velocity and the momentum, so you get twice the projection angle. And to this, you have other related quantities. So for example, so-called radiation pressure. So this is the pressure that radiation exerts when it falls on a surface, which is very small. That's why if you are outside and the sun shines, you don't get blown away because it's very tiny. However, it is measurable. And in fact, these are very small letters here, but if you can read them, it was actually measured well over 100 years ago, 1901. In fact, a year after Planck wrote his law. Interesting kind of from point of view of history. And it's published in this paper if you are interested to see how it works. And there are actual applications of this radiation pressure. So for example, this satellite, which is here shown in reality, or a model of it, I think. And here in some kind of artist impression. But basically, this is a solar sail, which you can use to push the satellite and without expending additional energy. And of course, it has been mainstay in science fiction, as I'm sure you are aware, and has been planned for many kind of spaceships and so on in the future. But for the moment, this is what exists in practice. All right. So there is another kind of quantities, a whole set of quantities that are useful in certain contexts, and we'll come back to them in a little bit. So these are called so-called moments of the momentum field, or moments of the radiation field, sorry. So the zeroth moment is just the mean intensity. So essentially you take the intensity and you say, okay, I'm averaging over all directions. I don't care if it's flowing this way or that way or that way. You just take the average, whatever is flowing in any direction over the whole solid angle. But then I divide by 4 pi just to average, because the total solid angle is 4 pi. That's the area of a sphere. And so this thing, of course, if you compare to the formula before, it's also, this is usually called J nu, by the way. So this is the average intensity regardless of direction, and it's related to the energy density of the photon field with some normalizing factors which make the units correct. And then if you do this same thing, but in a kind of cylindrically symmetric way, so you are projecting in cylindrical coordinates, so then in axisymmetric way, this will look like this. So it's just the intensity integrated over the angle of the axial symmetry with respect to the axial symmetry, and there is some coefficient. You can also define first moment. So the first moment, which is usually called h nu, this doesn't mean anything, it's just notation. This is just the intensity, but now in particular direction. So there is additional cosine theta from the projection, because you have the area and then it's projecting in particular direction. So there is a cosine between them. And again, averaged over all the solid angles, the total solid angle. And this is the same as the flux, but divided by 4 pi. So they are not exactly the same quantity, but very closely related. And you can also do it in axisymmetric in slightly simpler form. And then you can do second moment, which is actually the radiation pressure, or proportional to the radiation pressure, I should say. And the second moment, not very surprisingly, is the same thing, but projected with cosine square, because it's velocity square. And so on, you can go to higher moments. So in principle, if you know all the moments, that you know everything about the radiation field. Literally everything that exists in the radiation field, you know if you know all the moments. In practice, you never know all the moments because they're infinite number, so that's not very useful to do. But as we'll see later when we discuss radiative transfer methods and how you do it in practice, there are certain methods which use this moment expansion and then only use the first few moments and then some kind of additional condition, which is called closure, to ignore the higher order moments. So there is some approximation involved, but this usually is good enough approximation. Okay. And lastly, before we have a little bit of time for questions, a few examples. So for example, let's say you have isotropic radiation field. Isotropic just means it's the same in all directions. So this will be, for example, the CMB, right? CMB is the same whichever way you go, as long as you're not moving with respect to it, which is another thing. So in this case, the intensity is constant in all directions. And if you plug it to the formula that we had before, which was this one, so if you have intensity that's constant, obviously the integral becomes very easy because you take the intensity out and the integral of the solid angle in all directions is just 4 pi, so it cancels out. So the average intensity is just the intensity, not very surprisingly, because it's all the same. But if you calculate the other integrals, so for example, you can calculate this one as well and this one, and that's also not too difficult to do. And what you get is that the mean intensity, which of course is the energy density divided by 4 pi and times c, is the same as the intensity, which is the same as, well, some constant time the pressure, radiation pressure. So if you compare the first and the last expression, you cancel the c's, you cancel the 4 pi's, and you get that the pressure is the energy density divided by 3. And that should be familiar to you because that's the radiation equation of state. So that's where it comes from. So that's true for CMB or for any other kind of isotropic radiation. On average, that's the pressure is related to the energy. If you want to calculate the middle integral for the flux, what you get is actually 0. And the reason is simply because if you have isotropic radiation, whatever flows this way, the same thing flows the other way, right? Because it's isotropic, so it's all the same. When you average out something that's flowing exactly the same both ways, you get 0. That doesn't mean there is no flux. It just means that the flux on average is 0. But if you take, for example, one hemisphere, you get flux is pi time I nu. So that's why, for example, if you take the sun is isotropic. It emits the same in all directions, well, roughly, if you ignore the details about the sun. But the average flux is not 0. Why? Because you're only seeing the face of the sun. You're not seeing the back of the sun, right? So you are interested only in the hemisphere. Okay. So another slightly more complicated, but still very simple case. You have direction along array, which again will come back again when we discuss radiative transfer and ray tracing. So you have direction, unidirectional radiation, it all goes one way. In this case, you have that the intensity is just the intensity, and there is, you can indicate the unidirection with some kind of delta function of direction. So just when for a particular direction it becomes 1 and everywhere else is 0. So in this case, again, integrals are very simple because integrals of delta function are very simple. And you get that the pressure is the same as the energy density of the radiation. And finally, one interesting case, slightly more complicated, but not by much. You have, when you have a bundle of rays, so they're rays that can travel more or less in the same direction, kind of together. If you take a little area through which they travel, so that's a bit complicated diagram, but we'll go through it little by little. You have that the power going through this area is the same as power through this area because whatever rays go through here, they pass through that one as well. So then when you compare the two expressions, this is the intensity times the cross section. This means the area, then the solid angle and the frequency. And this should be the same for the other area. So this is 1 and this is 2, and they are the same. But then if you remember that the solid angle is actually the area over r squared, the distance, and the other solid angle is the area over r squared, which is the same distance, and you plug it into this expression, you see that I is the same along the bundle of rays. So if you are just a ray, here your photon traveling with that ray, intensity stays constant, never changes, as long as you don't have any absorption or scattering or something else happening along the way. So you have constant intensity. Well, if you do the same for flux, flux is of course, well, you need to do a different integral, and if you do that, you get that the usual expression that flux goes as 1 over r squared. So flux diminishes over time, over distance rather, because it gets spread out over a bigger and bigger sphere, while intensity along array is constant. Okay, before we go on, any questions? So these are the most fundamental and the most boring part of the lecture, but it needs to be said because it gives you well, the language in which we'll be talking. Any questions up to now? Too simple or? Okay, well, let's hope this means that everything is understood. All right, so coming now to the main topic, which is the radiative transfer. So what is a radiative transfer? Basically, radiation, first of all, is the main channel through which we obtain information about the universe. If you try to observe the universe, almost all the information comes through radiation. There are a few exceptions. You could have particles occasionally, neutrinos, gravitational waves. There are a few other things that are not radiation, but most of it is radiation. It doesn't matter what kind. Would it be X-rays, visible, radio, whatever it is, it's all radiation. And that radiation, as it goes through stuff, which of course there is always in the way, regardless of even in the emptiest space in the universe, there is some gas or something, plasma, something. There are things that happen to it. So there is one example with the Earth here, but it's the same principle. So you have the incoming radiation, and the incoming radiation, first of all, can get absorbed by the atmosphere, because atmosphere is made of gas and particles. Some of it could also get reflected by clouds and other things. That's why it's a little bit cooler when it's cloudy, right? Because some of the radiation gets reflected back. Some of it could get to the surface and then get reflected. And some of it could get absorbed along the way. So what gets here is a bit less than what you started with. And how you describe all these processes of absorption, emission, and scattering is radiative transfer. Basically, the radiative transfer is how radiation interacts with matter along the way. If there is no matter, if it's complete vacuum, of course, there is no radiative transfer. It just travels. Intensity is the same. And that's what we just talked about a moment ago. And there are some other effects which we won't talk about much, but in principle, you can have also polarization because sometimes when the interaction happens, it changes the polarization of light because of other physical processes. And there is also, for cosmology, one thing that's important is redshifting, because universe is expanding and light is shifting to the red as this happens. Okay, so how do we describe the radiation? So let's start with the simplest possible case, which is radiation propagation in vacuum. And now you'll say, okay, but why that? Because then this is exactly the case when you don't have radiative transfer, right? But it's simpler, and we want to start writing the equations, and starting from this point is easier, and then we can go from there and make it more complicated. Okay, so the first thing that you can notice is if I write the photon distribution function, the photon distribution function, photons are conserved along the way because they are traveling in vacuum. So whatever photons you have somewhere, the same ones will be a little bit later. Because there is nothing happening, right? They're just traveling in vacuum. So you cannot either lose any of them or create any more photons. So this means that the probability distribution a little bit later will be exactly the same. Since whatever density you had, it stays the same. That's density in 6-dimensional space, by the way. It's not the density in physical space. They could still change in terms of momentum or other things, but in 6-dimensional space, it stays the same. And a little bit later, of course, the position will be the wave vector times c times the time. So this gives you how much they got forward. And of course, the time will be a little bit later, and the momentum itself stays the same. And this kind of expression you can expand in Taylor expansion, so you get around the original position. So the original position at x, p, and t, you have, of course, just the same distribution function. And then at dt, you get the derivative of the partial derivative with respect to time and the gradient with respect to space. So from the two terms, so that's what you get. And when you compare the two sides, you see that this is the same as that, which means that this better be zero, otherwise it's mathematical nonsense, right? So it cannot be. So, and since dt definitely not zero, since time passes, this means that whatever you have in the brackets is zero, and you get the radiative transfer equation. So that's what's describing the transfer of radiation in vacuum. And once again, the distribution function is not constant, but what is constant is this combination, so the flux through the surface and the change in the density with time. When you add them up, you get zero. Then you can rewrite the same thing also with the intensity, remembering that the intensity and the distribution function are exactly the same thing with some constant in front. So you can write the same equation for the intensity. And then if you remember your vector algebra, which, well, you may or may not, but I'm sure you can if you try. So what you get is that this is actually the full derivative of the intensity, because you have the partial derivative plus the gradient. So this is the full derivative ddt. So the radiative transfer equation in practice is just di dt equals zero. The full derivative equals zero. So distribution function or the intensity, whichever you like, is conserved in time, but conserved in the sense of full derivative, not in the sense of partial derivative. In fact, if you want to be more specific kind of mathematically, that's called, it's a version of something called Liouville's theorem, the conservation of phase space density over time. But anyway, so that's the radiative transfer equation in vacuum. And the last bit to note here is that speed of light is typically very high, right? It's much higher than most things you can think of. So this means that it's usually faster than ionization front speeds, faster than how the effects of the radiation is propagating forward. So this means that first term is actually usually much smaller than the second term, because the first term is divided by c and the second term isn't. So very often the radiative transfer equation reduces to just the second term equals zero, because the first term is very small. That's not always true, but often it is, or at least is good approximation. Okay, so now coming to the more interesting bit, which is how you do actual radiative transfer. So now you have to account for the fact that some of the radiation may get absorbed and some more radiation may get created along the way, because you are passing through matter. This matter could be shining or it could be absorbing, and both, or it could be doing both at the same time. So how do we account for this? Well, we say, okay, so we are still writing this di dt. In fact, di ds we call it because you can divide by c and take it as a path length rather than time. So this could be written to be equal to kind of in a quasi-equation for the moment as something we call sources, so some additional sources of radiation that may emit more radiation as it passes through, and some sinks where the radiation gets absorbed. So usually you can have both or one of them depending on what material you are passing through and what kind of radiation as well. So the sources typically are described with something called spontaneous emission coefficient, or just emission coefficient, which the specifics of it depend on what kind of process is important for the emission of the radiation, right? So this could be, for example, atoms that were excited and now they get de-excited and emit radiation. or they could be, it could be some non-atomic process, which there are many, could be, for example, due to accelerated charges, so synchrotron radiation or Bremsstrahlung radiation and so on, whatever it might be, but you can describe it with some kind of emission coefficient, and the units for that is energy per unit volume and per unit frequency and per unit solid angle. Or you can describe it with emissivity, which we usually call epsilon nu, which is energy per unit mass, per unit time, per unit frequency. And the two are closely related. This emissivity times the density over 4 pi. It's like the average of the emission coefficient. So what are these things? As I said, they should be calculated for a specific radiative process. So we are not going to specify them now because obviously we are doing it in general rather than for specific case. What about the sinks? So now the sinks are a little bit trickier, or at least more interesting to discuss at this point, because they depend only on the matter rather than what kind of process is doing it. Although it depends also on the process to some extent. So the sinks, you can think of it that way. You have a volume, and the photons enter that volume, which has certain length and certain cross-section. So photons enter and then pass through the volume, and there are fewer photons coming out on the other side because some of them get absorbed. So how many would get absorbed? Well, you can think of it as some kind of cross-section. So this is where the process comes in. So what's a cross-section? Well, cross-section is, for example, well, what is my cross-section? My cross-section is whatever you see, right? The area that you see. So if there was any light coming this way, some of it won't pass through because I will be on the way, right? So the area that I'm projecting is the cross-section. And you can do it for anything else, right? The cross-section of the desk is just the area of the desk. For other processes might be a bit more complicated because, for example, atoms are not solid, so the cross-section of an atom depends on how the photons interact with that atom, but you can always calculate it using quantum mechanics. Maybe it's not very simple, but you can calculate it. Okay, so you have the cross-section times the number density of the atoms, because obviously the more number densities the more atoms you have per unit volume, the more likely is for photons to hit one. So imagine there is a whole room full of people, right? And the more people there are in the room, and if you try to run through and you are the photon, right? What is the chance to hit someone? Well, the chance is, first of all, depends on, well, how big the people are, right? So this is the cross-section, but also how many people there are actually in the room per unit volume. Of course, people are not stuck to the ceiling, so it's more like two-dimensional thing, but you can get the idea. So, and then you multiply by the volume to get the total number of atoms. So the total number of atoms times the cross-section just gives you the total cross-section, because there's the chance to hit something as you go through the volume, right? So if I run through the room, what is the chance to hit someone? Well, it depends on how many people there are. So, and of course, the volume is just the area times the distance as you go through. And absorption probability then is just the cross-section times the number density times the distance, because you need to divide the total cross-section by the total area. So this gives you, okay, if I have, this is my total cross-section, and I take the cross-section of each one of you and add them all together, there's the chance for me to hit something if I run through the room, right? So that's what the absorption probability is. So you need to divide by the total area, and then you get chance for hitting something. So you can write this as ds over L nu, where L nu is something called mean free path And mean free path is a very simple thing. So if I'm the photon and running through the room, how far can I get on average before I hit someone? That's the mean free path, right? Literally. So the mean free path, as you can, if you compare the two formulae, the mean free path is just 1 over the cross section times the number density of atom. And there are other ways to write the mean free path. You can write it as 1 over the density times something called opacity. So opacity is basically how thick the material is, how easy it is for the photons to pass through or not. So it depends on the material. Or you can write it as 1 over alpha, which is called absorption coefficient. So if you use the last example, the last case, because it's the simplest, you can write the radiative transfer equation with only absorption as alpha times I nu. Why is it times I nu? Is because alpha gives you a chance to absorb something, but then you need to multiply by the total intensity, because the more photons there are, the more photons will be absorbed, obviously, right? So if you have fewer photons, you absorb fewer photons because there are fewer to be absorbed in the first place. So it needs to be proportional to the number of photons. And then the total equation then becomes sources, which is J nu, the intensity, the specific intensity. And then the absorption is alpha nu times I nu. So this is the full radiative transfer equation. Now it seems like a very simple equation, but of course, as with all things, it's not as simple as it looks. So that's why we have been solving it for many years, but we'll come to that later. But one thing that's already obvious, it's not that simple simply because you need to know all these things. You can solve for I nu, but you need to know, okay, what's emitting. So you need to know the properties of the material, how to calculate the various processes that are occurring and so on. You need to know the properties of the absorption properties of the material, and then you need to worry how to solve the equation in the first place. Okay. So before we start solving the equation, let's define one very important quantity, which we'll mention again and again, which is called optical depth. Optical depth you probably have heard already at some point or another, or if not, well, that's the definition of it. So optical depth is basically you take the absorption coefficient and then you integrate it over the path. So what's the difference from absorption coefficient is absorption coefficient is kind of per unit length. So it's the thickness of the material, how much it absorbs, but then the optical depth measuring also taking into account, okay, how much material there is in the first place between here and there, right? So optical depth, if you follow the units, which I'm sure you haven't, but it's fine, it's actually dimensionless because this has dimensions of length and this has dimensions of 1 over length. Because if you remember from before, oops, to do that. If you remember from this absorption coefficient is 1 over the mean free path. Mean free path is length, so it's 1 over length, right? So when you multiply the two, you obviously get dimensionless number. And that's one of the reasons, maybe the main reason why optical depth is really useful, because it's easy to work with, it's dimensionless quantity, and it tells you how thick the material is to the light, how much gets absorbed. And using the other relations, you can also write it in terms of opacity times the density times the path length, or as the path length divided by the mean free path. So mean free path tells you essentially it's inverse of the optical depth. So it tells you basically optical depth tells you how many mean free paths you can go through before you are likely to be absorbed. Optical depth of 1 would mean that well, you can go 1 mean free path. So that's the other definition of the same thing. And if you integrate along the photon path length, you get that the actual optical depth, not differential, is the integral of the opacity coefficient over the path. So now, if you consider what are the possible cases for the optical depth, there are three obvious ones. Remember, this is just a number. So when I say something is bigger than 1 and smaller than 1, I don't need to specify what is the 1. 1 is 1, right? It's just a number. Doesn't have any units. So something bigger than 1 is called optically thick. Something around 1 is kind of in between. It's a border between optically thick and optically thin. And then much less than 1 is called optically thin. So if you are in the optically thin regime, usually you don't need radiative transfer. So that will be the case for visible light in this room. Right, there is air between me and you, but you can still see me clearly because the visible light doesn't get absorbed much by the air. If you are in the optically thick regime, then light usually doesn't pass through, it gets all absorbed because optical depth is very high. And in this case, usually you have to use radiative transfer, but you can use certain approximations like diffusion approximation because light gets absorbed and then maybe emitted and kind of slowly diffuses through. And what's the most interesting case from our point of view is when you are in between. And that's also the trickiest one to solve because when you are in between, you both need radiative transfer and, you cannot use simple approximations. Okay, so optically thick is basically illustrated here like a brick wall, right? Nothing passes through. So if I try to look through the wall, right, obviously I don't see much because photons don't go through. Then borderline will be more like this. Maybe not very typical for India, I don't know. Well, sometimes I guess for if there is smoke or something, but anyway, you have seen it or at least seen it in movies or whatever. You see a little bit, but it's kind of, difficult to see. And then, optically thin will be when you can see everything. This is very Photoshop, but you get the idea, right? It's very clear, you can see, it's very nice. All right. So how can you solve the radiative transfer equation? Well, it's actually complicated, but you can write some simple kind of formal solutions if you want. So just to remind you, I put the radiative transfer equation here that we are trying to solve. So some simple cases. So if you just have emission, so the second term is out, there is no absorption. You just emit radiation. As the light passes through, you get more and more and more. So in this case, it's very easy because you just integrate the emissivity along the path, and that's what your final intensity is. So what does this mean is you have the intensity that you start with, that you enter the cloud, and then as you go through the cloud, because the cloud is only emitting and not absorbing, you get more and more and more intensity because you are adding additional photons as you go through. And that's all, basically. So you just need to know, okay, so how fast am I adding the photons? If you have only absorption, so in this case, the first term is 0 and only the second term matters, then the equation is again relatively simple one. This kind of equation you can solve. Well, assuming that alpha is constant, but usually it's not too bad approximation. And if the alpha is constant, you just integrate this equation. And what you'll find out is because alpha gets integrated over the path length, you get that the initial intensity is the final intensity, but you need to put attenuation in, exponential attenuation with the optical depth. And the exponential comes from the fact that this is the solution of this kind of equation. Most general case, of course, it's neither one of those, but it's neither term is zero. So what do you do in this case? Well, you can divide by alpha. So alpha times ds is d tau. So you get I di. This should be di, by the way. There's a typo there. But di over d tau. And this is equal to, well, j divided by alpha, which is called usually s, and it's named source function. And I, because, well, you cancel the alpha there. So then this can give you, there is a formal solution of this kind of equation, which is slightly more complicated than this kind of equation, but you can solve it if you remember your calculus. If you don't remember, you look it up or use Mathematica or something, and you get it. So basically, the formal solution is that you have the initial radiation that enters the region of space that we're interested in. So this initial radiation gets attenuated over time as it passes through the cloud because of the absorption. But then there is this combined effect of some additional attenuation, but also emission because of the cloud, since it's emitting as well as absorbing. So this whole effect is this source function, and then it gets integrated over the optical depth through the cloud. So if you assume the source function is constant, just to keep things simple, and that's not always true. In fact, almost never is true, but sometimes could be roughly true. Then, of course, you can take S outside. Then the integral becomes very simple because anyone can integrate an exponential. And what you get is this simple equation. So you have that the intensity at the end is the initial intensity attenuated through the cloud. And then you have the source function times this function of the optical depth. So now you can have some specific cases of this, specific limits. So if you have high optical depth, what happens? Well, for high optical depth, you have that this exponential is 0, or very small anyway. This exponential is, well, just as 0 as the other one. And you have that the intensity is the source function. So what happens basically is that for high optical depth, initial intensities that enter the cloud is forgotten because it's all gone by now. And all that remains is some combination, some balance between whatever the cloud emits and whatever the cloud absorbs. There is some balance which is described by the source function. If you have low optical depth, the other limit, then you get the exponential is 1 minus tau. So you can plug this in here. So 1 minus tau is just tau, and you get this kind of expression. You don't need to remember this, of course. It's not that important. But what is important is to remember that low tau does not mean you can ignore everything. Low tau does not mean, okay, forget about any effects from matter. That's not true. Matter still changes. It just doesn't change too much. So you still have mostly the initial radiation, but there is also a little bit of effect from the optical depth. So that's what happens if you are in a cloud, right? You still see the sun, but you don't see the full sun. There is still some effect on the sun. All right. How are we with time? There is still a little bit. So let's cover this last bit, and then we'll have time for questions, and we'll stop for the break. So how do we do cosmological radiative transfer? How do we do radiative transfer in cosmological context for our simulations of either ionization or maybe at later times whenever the region is reasonably optically thick? So radiative transfer equation, first of all, in cosmological context, need to be modified because of the expansion of the universe. Up to now, we pretty much ignored the expansion of the universe because we wrote it in general terms, and in general terms, well, the medium usually is not expanding, but the universe is expanding. So first of all, you can show, I'm not going to do it now, but it's relatively easy to do, that intensity divided by the cube of the frequency is constant. So if this is true, then you have that the derivative with respect to time of that is 0 because it's constant, right? So obviously you can set it to be 0. I mean, you can show it to be 0. And then if you write this and remember what I was in the first place and take the derivative, you get that this is the time-dependent term, di dt. Then you have the spatial gradient times the wave number. And then you have another term which comes from the fact that frequency now is not independent of time because of the expansion of the universe. There is redshifting. So there is this additional term which contains the Hubble constant and, well, some combination of I and derivatives with respect to frequency. And so this is the equation of radiative transfer in an expanding universe. Obviously, if the universe is not expanding, this will be 0. And you go back to the original equation in vacuum. So we are not completely crazy, right? They are consistent. And in presence of matter, you have exactly the same equation, but now you put, like we did before, some additional, if there is some additional emissivity and some additional absorption, which you need to account for. So this is the full equation of radiative transfer in cosmology. So this here is the cosmological term. If the universe is not expanding or the medium, then you don't have that. Everything else is exactly the same as it was before. All right. This may actually be a good time. Good time to stop. So any questions? Come on, it can't be that clear. There must be something you want to ask. Yes.
Hi. Is there any intuitive way to understand that condition there? I knew over nu cube is constant for cosmological expansion.
Yeah, basically it's, well, I don't know intuitively, but basically it's comes from, what's the easiest way to? It comes from conservation of photons, essentially, in the phase space. And you can calculate from the equations that I gave you at the beginning that essentially, well, it's long way, oops, long way. I think the easiest way is probably to start from here. So you write this equation, but not for a bundle of rays in a direction, but for three-dimensional kind of. And if the space is not expanding, then it's easy. I mean, it comes down to the same thing, but if it's expanding, then you get redshifting. And so you're stretching the same energy into bigger volume or yeah, you can think of it as, yeah, stretching the, I don't know, intuitively it's a bit, not sure how to explain it most easily. I mean, mathematically it's easy to derive, but intuitively, Not sure there is. Okay, let me think about this, how I can explain it more easily, but you can also work it out just from the equation directly. Mathematically, it's easy to do, but intuitively, I'm not sure. Okay, I'll come back to that. I'll think a little bit.
Okay.
Anything else? Yes. Yes.
Last equation, both of the term is in positive or like
Sorry, both of
absorption and the J term?
that's the absorption, that's the emission. Yeah.
Yeah. So both have positive sign. There should be one negative, one positive.
Yes, I think there might be a typo here. Yes, we wrote it this way. Okay, yes, good point. This should be negative. The way we defined alpha, this should be a negative because it's absorption, yes. Yes, there should be a minus sign here. That's correct, yes. In fact, there are some, I mean, we won't get into that, but there are some strange cases when you can have negative absorption, which is also known as stimulated emission, and then you get lasers and masers and so on, but we are not going to that. In principle, but in this case, of course, yeah, then alpha is negative. There's still negative sign, but alpha is could be negative in some kind of special cases. Any other questions? Okay, so let's break for coffee and picture. And we'll come back. When we come back, I'll discuss in a little bit more how you actually do this in practice. Because at the moment, I mean, this is complicated equation. It's actually much worse than you think. So there are ways to solve it, but obviously we haven't got to that at all. So we'll discuss how do you approach this kind of problem. And then the practical tomorrow will be how you do these things in practice with one particular code that we wrote. By the way, how many people managed to install the code? Did anyone try? Please try, because otherwise tomorrow the practical will be very boring, because I'll have to show you stuff and you cannot do any of them yourself. So try to install it on your own computer. I wrote quite detailed instructions. If you see any problems, contact me or one of the people that are helping. And hopefully at least some of you will have it all installed. I know it's a little bit of a pain to go through the whole thing, but if you want to use it, that's the way to do it. So try to install it, and if you have it tomorrow, then we'll run some nice examples and all these things that I'll show you in the second hour, we'll be able to run in practice. So you'll get some nice pictures and you can play with it and change some things and see how it goes. Okay, so break, and then we'll come back in half an hour.